Welcome to Sano Seminar. Well, this will be the last seminar before the summer break. And today we have, as a speaker, we have Paweł Gora, who is still the postdoctoral researcher in the Sano team, working on extreme scale data and computing. Paweł is scientist. Paweł is also, well, as a scientist, he is a specialist in IT. He obtained his PhD in computer science from the University of Warsaw. And he was connected with many institutions. He contributed to also to something like Q Poland, and he is also a kind of entrepreneur, a kind of a philanthropist, and one of the institution which was formed by Paweł is Foundation Quantum AI and Quantum Poland. So I think that his contribution to making quantum computing popular, not only on the academic level, but also among people from secondary schools in Poland is very important. And today, Paweł will give us a kind of introduction to quantum machine learning. So, Paweł, screen is yours.
Okay, thank you. Thank you for the invitation. It's my pleasure to give this talk during the seminar at Sano. Thanks for the introduction. Indeed, I have several hats now because I'm the founder and CEO of Quantum AI Foundation, which is a non-profit organization supporting education and research in new technologies, especially quantum computing and AI and intersection of quantum technologies and AI. One of the projects supported by the foundation is Q Poland, so it's a community of quantum enthusiasts here in Poland, being a part of an international organization that's called QWORD. And indeed, I'm still formally connected with Sano. So formally, according to the contract, I'm a volunteer, but I was a postdoctoral researcher in 2024, but I still have connections with Sano and can consider myself as a part of a Sano family. So it's even greater pleasure to give this talk to you about the quantum machine learning. So actually it will be an introduction to quantum machine learning. So I will start from the introduction to quantum computing, actually. So let's try to answer the question what the quantum computing is. So the simple answer is that these are computations according to the laws of quantum mechanics, but it still doesn't explain a lot. So in both phrases, quantum computing, quantum mechanics, we can see this word quantum. So what does quantum mean? So in physics, a quantum is the minimum amount of any physical entity involved in an interaction. And fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. This means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. All right, and how it's related to computing, actually. So we know since more or less the beginning of 20th century that our world is quantum. It's governed by the laws of quantum mechanics at the bottom. And as computation is a physical process, it is governed by the rules of physical world, which is inherently quantum, right? So we can talk about algorithms, about computational complexity, we can prove correctness of algorithms, but at the end of the day, we would like to run our programs implementing the algorithms on the real quantum or the real physical device. And these devices are governed by the rule of the physical world, which is inherently quantum, so by the rules of quantum mechanics as well. And one of the consequences is the famous Landauer principle, which says that there is a minimum possible amount of energy required to analogically irreversible manipulation of information, like erasing one bit of information. And here you can see the formula. We have the Boltzmann's constant involved and the temperature of the environment. So when we do some computation, we perform computations on our computer, we cannot do it for free, right? So there is a minimum energy that we need to do it. It's very small, but there is still a lower bound, which is very important. And so how do we exactly know that our world is governed by the rules of quantum mechanics? So because at the end of the 19th century, many physicists, most of the researchers believe that we know almost everything about our physical world, or at least about the rules governing our physical world. And there were just several open problems, open questions that were expected to be solved relatively soon, and with the knowledge that the scientific community possessed at that time, so at the end of the 19th century. But at the beginning of the 20th century, there were several discoveries that proved that it was wrong. And there was a famous Max Planck's postulate that says that electromagnetic energy could be emitted only in quantized form. So here we can see the formula. We have an energy of a photon. We have a Planck's constant, we have the frequency of a photon or electromagnetic wave, and we have some integer numbers. This led, the formulation of this postulate led to many other discoveries that at the end, after about 25 years, led to the formalization of the field of science that is now known as the quantum mechanics. So just 1 year ago, we celebrated the 100th anniversary of formulating the quantum mechanics, and that's why the 2025 was the International Year of Quantum. So we know that our world is quantum. We know that our computations on physical devices are governed by the rules of physics and quantum mechanics. So there can be some other implications of this. So Richard Feynman, a famous physicist, formulated a statement that there is nothing that can see in the physical laws that says the computer elements cannot be made enormously smaller than they are now. And in fact, there may be certain advantages. Researchers observed that indeed they were able to build smaller and smaller devices with higher density of integrated circuits or transistors. Perhaps you have heard about something that's called Moore's law, that says that the number of transistors in a dense integrated circuit doubles about every 2 years. So at the beginning, when the Gordon-Moore's law was observed or formulated, it was even faster, so it doubled once per about 1.5 years. Now it's more like once per 2.5 years, or maybe even slower. But this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. But in 2015, the Gordon Moore himself said, "I see Moore's law dying here in the next decade or so." And Intel, the company producing computing processors, also observed that the pace of advancement has slowed. So this doubling is no longer once per 2 years, but once per 2.5 years, more or less. But it was also concluded that this trend will continue for some time. But the question is, can this trend continue forever? So if this trend will continue, then in 2000 or around 2035, 2040, the size of a single transistor should be of a size of a single atom, more or less. And in such a small scale, would not be able to perform computations using the transistors that we know currently. So already many years ago, at the end of the 70s, beginning of 80s of the 20th century, people started thinking how we could perform computations on such a small atomic scale. And again, Richard Feynman said that we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function, the ones move around, the zeros move around, and finally, along a particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But can we do it? So that was the question posed by Feynman. And as I'm talking today about quantum computing, quantum machine learning, I believe that you can guess, or you know, that we already have some initial quantum devices that some people call quantum computers. Some researchers, especially physicists, do not like when these devices are called quantum computers because they are still imperfect, they are still very noisy, they have small number of qubits, limited coherence time. So some people just do not like telling that these devices, contemporary quantum devices, are quantum computers already. But we can say that we already have some quantum devices that could conduct computations, perform computations according to the laws of quantum mechanics. And here you can see an example in the figure. On the left figure, you can see a picture of the bristlecone, which is one of Google's quantum computers. And on the right is a cartoon of this device with each X representing a qubit with nearest neighbor connectivity, right? So we have some qubits and some of them are connected. And this connectivity in quantum computers is also important. Okay, so we know that we have, or we expect to have, some quantum computers soon. So what are the differences between classical and quantum computers? Why we just bother, right? So why we work on quantum algorithms and investigate how they can perform computations? When you think about classical computers, I believe that you know that the information on classical computers is stored using bits, right? So bit is an smallest unit of information that can be just transmitted or stored in a classical computer, and we have some logical gates that can be built thanks to transistors like and, or, not, and there are some logical operations, right? So these logical gates can take some logical values, true or false, as an input, and they can produce some outputs that can serve as inputs to some next quantum gates, right? So this is the basic idea. But in case of quantum computers, we have qubits and quantum gates. And now what is the difference? So qubits are quantum bits, and as you know, the state of a bit may have just one of two values, 0 or 1, right? So mathematically it's something relatively simple. It can be just an element from the set 0, 1. But a state of a qubit can be a superposition of state 0 and 1, which means that a qubit can carry some information about the state 0 and 1 at the same time. So mathematically, the state of a qubit can be any unitary vector of the two-dimensional Hilbert space over complex numbers. So when you even compare the mathematical definitions or the mathematical objects that can be stored using bits or quantum bits, you can already see the difference in the complexity of these mathematical objects as well. In case of classical computers, the state is determined, so we can know exactly whether the state is 0 or 1, and it can be changed from 0 to 1 and vice versa. And in case of quantum computers, so actually the superposition is determined as well, but if you want to get value 0 or 1, you have to do a measurement which breaks the superposition. And we only have some probabilities of getting 0 or 1, and this probability depends on the state of a qubit, so this unitary vector in two-dimensional Hilbert space over complex numbers, and quantum gates just modify qubits and modify the probabilities of getting 0 and 1 after the measurement. And here you can see just let's say mathematical representation of a state of a qubit. So here you can see some states 0 and 1. So this 0 and 1 in this strange bracket is a so-called Dirac notation or ket notation. So we call it 0 ket or 1 ket. And actually we should think about the states 0 and 1 not as just numbers. So at the end, after the measurement, we interpret them as numbers. But in terms of quantum mechanics, and before we perform the measurement, we should rather think about them as vectors. And they just cannot be any arbitrary vectors, because they should be a basis state, a base of this two-dimensional Hilbert space. So it should be an orthonormal base of a quantum system. So we can also interpret the 0 ket and 1 ket as just vectors 1, 0 and 0, 1 in just two-dimensional space. And A and B are complex numbers. So squares of their amplitudes are probabilities of getting 0 or 1 in a measurement, so that the sum of the squares should be equal to 1. And there is a property of quantum mechanics that when we multiply both these numbers by a unitary vector, we actually do not change the quantum state. We do not change the physical properties of this quantum state, which means that A and B can be transformed to spherical coordinates. So we can just find another complex numbers that just multiplied by A will give us a real number, and this already means that we should be able to represent the state using spherical coordinates, so we can represent it on a sphere that's called a Bloch sphere. If you are interested in mathematical transformation, you can see the formula at the bottom of this slide, right? So here there's a formula that takes two angles and returns the superposition of vectors 0 and 1, and we can do the opposite transformation as well. So here, as you can see, a state of a qubit can be any point on a sphere that's called a Bloch sphere, and state 0 and 1 are just antipodic points on this sphere. It turns out that quantum gates operating on a single qubit are just rotations of this sphere. So that's why sometimes we say that quantum computing on a single qubit is a journey on a Bloch sphere. And here you can see some notable examples of quantum gates. Probably the most popular one is the Hadamard's gate, and the Hadamard's gate takes, if it takes the state 0 as an input, it produces the superposition of state 0 and 1, which means that there is an equal probability, 50%, to get the states 0 and 1 after the measurement. And similarly, we have transformation of the basis state 1. X Pauli gate is quantum negation, so we transform the state 0 into state 1 and state 1 into state 0. There is a Y Pauli gate and Z Pauli gate. They are called X, Y, and Z gates because they correspond to rotations around the axis X, Y, and Z of the Bloch sphere. The rotations by 180 degrees. And these rotation gates can be also parametrized, right? So, for example, here we can see a rotation around the y-axis by an angle phi, and here we can see a formula for the transformation. So all these transformations are linear operations in this two-dimensional Hilbert space. So there are also matrices representing these linear operations. So actually these are even unitary operations. So the vectors of the length 1 are also transformed to the vectors of the length 1. There can be also quantum gates operating on more than one qubit. CNOT is the notable example here because it takes 2 qubits as an input, and 1 qubit is a controller for the NOT or operation, or this X Pauli gate on the second qubit. It's proven that any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of CNOT gates and single qubit rotations. So that's why the examples that I presented here are, someone can say, the basic fundamental gates that can also serve to build or at least approximate some other operations. Yes, so I've told you that every such a gate is a linear operation, so there is a matrix corresponding to this operation, and for every state represented as a vector, we can just multiply the vector by a matrix of this operation to get a new vector, and thanks to this we can know what's the result of applying a given quantum gate to a given quantum state, right? So in case of the Hadamard gates, it also represents a rotation of 180 degrees around the axis x plus z on the Bloch sphere, and alternatively it's a rotation by 90 degrees around the y-axis and then 180 degrees around the z-axis. And here is the Hadamard matrix corresponding to this transformation. For X Pauli gate, it's even simpler. So here is the Pauli X matrix, and it represents a rotation of 180 degrees around the axis x. And here is a parametrized rotation around the y-axis this time. So this formula and the matrix is more complex, let's say, but there's still such a formula depending. It's parametrized by the angle of the rotation, right? So it represents a rotation of p radians around the y-axis in this case. Okay, and as I said, we may also have quantum gates operating on more than one qubit, like CNOT gate. It operates on 2 qubits, and it performs the NOT operation on the second qubit only when the first qubit is 1, and otherwise it leaves the second qubit unchanged. And here is a matrix corresponding to this operation. So here we have a 4-dimensional matrix because in general, when we operate on n qubits at the same time using a single quantum gate, we actually do some manipulations, transformations in the 2 to the power of n dimensional space in this case, right? But all these basis states also correspond to some basis vectors. The true power of quantum computing comes with large number of qubits, of course, because let's think about an initial state in which we have only zeros at the beginning, then we apply the Hadamard's gate to all these n qubits, and then we have a superposition of state 0 and 1 for every qubit, and then when we do the measurement, we can get one of the possible 2 to the power of n-bit numbers as a result. And if we apply the Hadamard's gates, all these 2 to the power of n numbers should be equally probable as a result of the measurement, in theory at least. because there can be some noise that may also influence the results. So we can start using these n qubits. In some sense, we can store some information about these 2 to the power of n numbers at the same time, and then we can just modify the probability of getting each of these numbers by applying another quantum circuit, here represented by UF in this case. So it's some kind of a unitary operation. So why it is important? So one reason that I just mentioned, so on qubits we can process only one n-bit number at the same time, but in case of quantum computers, using n qubits we can process, in theory, we can process all 2 to the power of n-bit numbers at the same time. And another thing that's important is that in classical computers, results are deterministic. So randomness is actually a pseudo-randomness. So we may have some generators of pseudo-numbers, and we can control the values of the seed and replicate the results. But in case of quantum computers, we may have real randomness and easily sampled from probability distributions, which are difficult for classical computers. So by real randomness, we mean the randomness that actually exists in our physical world. It's still, let's say, uncertain what exactly is this real randomness, because there are different interpretations of quantum mechanics, and in some interpretations we live, or according to some interpretations, the whole universe is deterministic, but we observe only one of its realization. So it's let's say it's currently beyond our possibility to determine or even define what exactly the real randomness in the physical world is. But we have some good mathematical definitions, abstract definitions of probability, and for quantum computing it is sufficient. And quantum computing may have some interesting applications. You've probably heard about the Shor's algorithm for factorizing large numbers, and the problem, or the assumption that the problem factorizing numbers is difficult, was a fundament for the design of some popular cryptography algorithms. So thanks to quantum computers, we can potentially break some classical cryptography algorithms. But it's good to know that there's also something like quantum cryptography and quantum communication. So there are some other applications of quantum technologies that can help us transmit information in a safer way, in a sense that when someone reads the message that we have just sent, we can know about it, right? So we'll know about it, and we can change the communication channel, for example. Quantum computing can be also applied to solve combinatorial optimization problems that frequently occur in AI, machine learning, finance, transport, logistics. So when you think about it, almost the whole area of machine learning is about optimization. When we train neural networks, we explore the space of possible values of parameters, of connections, of weights of connections between neurons, and we just want to find a set of values for this way that would minimize our loss function on our training set. And it's similar in case of other machine learning algorithms. So usually there is a function that we want to optimize. So optimization problems frequently occur in machine learning. Sampling from difficult distributions, like Boltzmann's distribution is one of the examples. It also has applications in machine learning. Quantum random number generation. It can also be applied to generate really random numbers for the purpose of some cryptography algorithms as well. We can simulate quantum processes. It may find applications in discovering new materials, new drugs, searching in unstructured databases. We have square improvement thanks to the Grover's algorithm, generating art, like generating music, and so on. And I've also told you about quantum communication, and it's good to know that there's also another domain of quantum technologies that is called quantum sensing or quantum metrology, where we use quantum mechanics to measure some physical values with a very good precision, better than using some classical methods. We can observe progress constantly. So every year there is a progress. There are some interesting announcements. We have more and more physical qubits. We have better methods for error reduction. We have better connectivity between qubits. We have longer coherence time, and so on. So we can observe the progress. It's not as fast as the progress in the domain of AI. It's totally different pace of progress. But we can see that there is progress. There's a constant progress in this field as well. But contemporary quantum computers are still noisy, so we say that we still live in the so-called NISQ area. NISQ stands for Noisy Intermediate Scale Quantum, and it is the era in which the leading quantum processor contain about 50 to a few hundred qubits, but are not advanced enough to reach fault tolerance, nor large enough to profit sustainably from quantum supremacy. Okay, so we believe that we are still at the relatively early stage of the development of quantum technologies. But it turns out that even in this NISQ area, we can already think about some interesting algorithms and also the algorithms for machine learning. So when you think about quantum machine learning, it's good to know that in general, we can divide this whole field into at least 2 or 3 subfields, right? So here, this is a diagram taken from a nice presentation given by Maria Schult about quantum machine learning. Here in one dimension, we have types of algorithms, classical or quantum, and in another dimension, we have type of data, quantum or classical. So when we have classical data and classical algorithms, we have classical machine learning that you know, all these neural networks, large language models, decision trees, support vector machines, and so on. When we apply quantum algorithms to classical data, this is also called quantum enhanced machine learning. So we build quantum, or rather hybrid, so quantum classical algorithms that can solve some classical problems, or they can also solve some quantum problems from operating on quantum data, being trained on quantum data and not classical data. And it's also good to know that classical machine learning algorithms can be also applied to solve some open problems in quantum technologies, and they can contribute to the development of better and better quantum technologies. And actually these two fields, right, so rather the application of classical or quantum algorithms to quantum problems, are believed to be the most relevant, the nearest reasonable applications of this domain of quantum machine learning. But I will start from this field, from the quantum enhanced machine learning, in which we have quantum or classical or hybrid algorithms trying to solve some classical problems. So here, most of these algorithms are framed as using the term that's called variation quantum algorithms, or VQA in short. So these algorithms share a common structure where there is a computational task that is encoded into a parameterized cost function that is called ansatz. And this parameterized function is evaluated using a quantum computer. And there is a classical optimizer that trains the parameters in this variation quantum algorithm. So there can be different encodings. So we can encode the problem using different angles, right? So we may have rotation gates parameterized using or thanks to our encoding of our problem. But there are also some other ways of encoding data into such circuits. So such parameterized quantum circuits are called ansatz, as I said, and these VQAs have emerged as a leading strategy to obtain quantum advantage on noisy intermediate scale quantum devices. So I will later try to answer whether we have this quantum advantage here or not. But first I will try to tell more about this variation quantum algorithms. So as I said, the ansatz is the parameterized circuit that prepares the quantum state. Some ansatz architectures can be problem inspired, but some are rather general and problem agnostic. So usually when we have this parameterized circuit, we can also decompose it into a product of some number of unitary operators that are parameterized, sequentially acting on an input state, and there can be also some operators that are unparameterized in this case. Okay, so what are the required properties of the cost function that is computing using this variation quantum circuit? So its minimum should correspond to the solution of our optimization problem. It's useful to have the cost function that is operationally meaningful, which means that the smaller cost values indicate a better solution quality. It should be possible to efficiently estimate it by performing measurements on a quantum computer and possibly performing classical post-processing. An implicit assumption here is that the cost should not be efficiently computable with a classical computer, as this would imply that no quantum advantage can be achieved with the variation quantum algorithms. And it must be trainable, which means that it should be possible to efficiently optimize the parameters using some kind of optimization algorithm. This is a hybrid approach. This is a hybrid algorithm in which some computations are performed using the quantum processing unit, and so actually most of the computations are performed on a classical computer. So the quantum processing unit just takes a set of parameters, so representing the encoding of the problem that we want to solve, and it returns a set of measurements. And the classical processing unit takes a set of measurements and calculates the energy value. So it's usually some kind of averaging over multiple runs of this evaluation of the quantum circuit. It performs the optimization procedure, so it calculates what a new set of parameters should be and determines whether we should stop this training process or not. And here just some examples of the optimization procedures that can be used. So choosing a right optimization method may decide whether we'll succeed or not, and it's pretty difficult, so there are no silver bullets here. So why these variational quantum algorithms are good for the NISQ area? So what are the disadvantages of this area of noisy intermediate scale quantum devices? There is a lot of noise. So every time we apply a quantum gate, there is a substantial chance that we'll apply a bit different gate. And this is just one of many flavors of noise that we can get, because when we do the measurement at the end of computations, there can also be noise in the measurement process. The qubits live for a relatively short time, so after some time we can be pretty confident that whatever information was stored in the system, it is lost now. So the number of operations and number of quantum gates that we can apply to a single qubit is limited. And we have a relatively small number of qubits as well. There might be also some restrictions on which qubits can interact with each other, which qubits are connected, right? So I showed you at the beginning this design of the topology of connections in this Bristlecom computer from Google, and then you saw that not all qubits are connected and not all qubits can be entangled, so not everywhere we can apply the CNOT gate. So there can be some restrictions because of that. So of course we can use only small number of operations per qubit. This is the so-called circuit depth. We can't assume that everything will go according to the plan and there will be no errors along the way. So because of the noise, it's almost certain that there will be some errors. But even if there are errors, we should still get a reasonable answer. So we call it robustness. And obviously we can't use more qubits than we have, right? So these variational quantum algorithms are pretty flexible when it comes to the circuit depth. So we can initially use a pretty simple ansatz, so pretty simple parameterized circuit with relatively small number of parameters, and we may want to keep the circuit very shallow. But once we have a machine which allows for a deeper circuit, we can use more sophisticated ansatzes and the performance might increase as a result. These variational quantum algorithms have been shown to be somewhat resistant to noise. So even in the presence of noise, so up to some levels, it can give correct results. So some people even claim that a pinch of noise might help with the optimization process because it can help to escape local minima. So if you know something that's called dropout in the classical machine learning, when we randomly remove some connections or neurons from our neural network, then it works similarly, right? And this we just introduce some noise, and it is believed to help escape from local minima and improve the generalization properties. So in classical machine learning, this dropout technique is considered as one of the most successful regularization techniques to prevent overfitting and to ensure that on the test or validation set, our results will be as good as on the training set. So and it is believed that in this case, this noise in the contemporary noisy intermediate scale quantum computers can serve a similar purpose. And of course, it's very interesting and open question whether we can simulate this quantum noise using a classical computer, because if we could do it, then perhaps we still do not have quantum advantage, but perhaps we can improve our classical machine learning algorithms using just classical computers by just introducing some quantum noise, right? So this is also one of the reasons why it's good to study quantum algorithms, even though we still do not have very powerful quantum computers. And here are some examples of these variational quantum algorithms. There are mainly two families, QAOA, quantum approximate optimization algorithm, and there are several variants like recursive QAOA or warm start QAOA, when we start from a solution that is already quite good and try to improve it. And there are also variational quantum eigensolvers and their variants like filtered VQE, layered VQE, and combination of these techniques. These approaches can be also combined with even more hybrid architectures like quantum neural networks. So this image was taken from another interesting presentation given by Piotr Gawron a few years ago. So we have some hybrid neural networks actually, in which there are classical neurons, classical nodes, and quantum nodes, parameterized quantum nodes. In this case, when we train such a model, we also perform something like a back propagation. So we have to calculate the gradient. And in case of a quantum gradient, we also just slightly modify the parameters that encode our solution and are used as parameters of our ansatz. So this is how this hybrid quantum neural network works. And there's also a nice master thesis prepared a few years ago at the Krakow University of Science and Technology, AGH, authored by Justyna Zawalska about solving the traveling salesman problem using TensorFlow Quantum. And actually she combined the QAOA, so one of these variation quantum algorithms, with a hybrid neural network, and there was an interesting encoding introduced, but one of the consequences was that there was a limited scalability, right? So she was able to solve relatively simple toy instances of the traveling salesman problem, but it was a nice demonstration of how these methods can work. There are also some other techniques like kernel methods. So if you perhaps you know from classical machine learning that in general kernel functions map input data into a higher dimensional feature space, enabling linear algorithms to perform nonlinear computations. So in some cases, it's easier to solve some problems and just distinguish points from different classes in a higher dimensional space. So here we can see some examples of typical kernel functions, and there could be also quantum kernels computed using quantum computers. So I've already saw research articles about quantum counterparts of all popular classical machine learning algorithms, even quantum large language models. There are already such papers recently. So it's definitely an interesting area for doing research. There are still many open problems. And for example, if we ask a question, can quantum enhanced machine learning achieve good results in some learning tasks? Then definitely yes. It has been proven on there are some research publications demonstrating this. But when we ask a question, can quantum enhanced machine learning outperform classical machine learning? The answer is, in my opinion, perhaps, but it's probably still too early. So most of the experiments that have been conducted were rather small-scale experiments. And even if there is an advantage, it's difficult to prove it, as many things in classical machine learning, right? So we cannot really prove that this model is the best possible model for a given problem, and there will be then no other model can outperform it, of course. And here are just some interesting applications from our domain, or actually our city, actually, because I heard that here in Sano there were already some research works about applying quantum machine learning neuroimaging for Alzheimer's prediction. And at the Jagiellonian University in Krakow, there is also a research group working on quantum machine learning for Earth observation. So they do binary detection of the pixels on the images in collaboration with the European Space Agency. So for sure, it's a very interesting research area. And now I also wanted to tell a few words about applying classical machine learning algorithms to solve some quantum problems. So this is another cell in this diagram presented by Maria Schult. So here are some examples: quantum state tomography, which is a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states, and also quantum feedback control and quantum circuits optimization. And here, if you are interested in more application, there is a nice review paper, quite long, but very good, or at least it was a good review of state-of-the-art a few years ago. It was co-authored by several researchers from the University of Warsaw. Anna David was the main author there, so I also encourage you to review it if you are interested. And I also wanted to show you another interesting example in which classical machine learning can be applied to enhanced quantum algorithms. So in this case, quantum annealing, which is another computing paradigm, quantum computing paradigm. So in quantum annealing, so we can use quantum annealing to solve combinatorial optimization problems that can be formulating as something that we called QUBO, quadratic unconstrained binary optimization. So here we can see the form. So we want to find values of x, so a vector, binary vector in n-dimensional space that would minimize the given function, right? So usually there is a part corresponding to the objective function that we want to minimize, and there is a part corresponding to satisfying some constraints. So in case of the problems like the traveling salesman problem, we have constraints like, so we need to ensure that every point is visited exactly once, or that a vehicle can visit only one customer, only one node in a graph at a given time, right? So these are just some examples of constraints that we may have, and if these constraints are not satisfied in our solution, then there is a penalty that should be scaled, right? So it should just lead to having very, very large value that would prevent our solver from finding such solutions. But it turns out that if the value of the parameter here, the parameter A, staying in front of the part corresponding to satisfying the constraints, is too large, then it dominates the whole formula, and it makes the further optimization process more difficult. So it's more difficult for the solver to find good solutions for the objective function that we really want to minimize. So sometimes we may think about setting lower values of the relaxation parameter, and even in some cases, we may even accept that, okay, some solutions that are returned by our solver, by our algorithm, are not feasible solutions, so they do not satisfy some constraints. But for the other solutions that satisfy the constraints, the quality of the solutions is better. And now the problem is, or the question is, how to find a good value that would be a good trade-off, that would assure a good balance between the feasibility of solutions and the quality of solutions, right? So the probability of satisfying all the constraints and the quality of results. And in the paper that is titled QROS, Q-bar relaxation parameter optimization via learning solver surrogates, the researchers applied classical machine learning to solve it. So first, they tested this method on the instances of the traveling salesman problem, in which the goal is to visit some number of nodes in a graph in the cheapest route or shortest time, depending on how we define the cost. So they defined the problem as a QUBO, and they applied, or they tested different instances of the graph G, and they tested different values of the parameter, of the relaxation parameter A, right? And then they solved these instances using a quantum annealer, and for each such an instance and each value, tested value of the relaxation parameter, they produce the probability of getting the feasible solution by just dividing the number of feasible solutions after some number of repetitions divided by the number of repetitions, right? They also calculated the average or expected energy, so the expected quality of the solution, and the standard deviation of the quality of the solution, because these solvers in quantum computing are stochastic. So that's why we have the average, and we have to repeat these experiments many times. And thanks to this, they generated a large data set, and they trained classical machine learning model that was a graph convolutional neural network with some interesting feature extraction architectures to approximate this value returned by the actual quantum solver, right? So approximate the probability of obtaining a feasible solution, to approximate the average quality of the solution and the standard deviation of the solution, right? So there was a loss function defined to minimize the difference. So once the model was trained, they were able to put totally new instances of the traveling salesman problem on which the model, this graph convolutional neural network, was not trained. And then they tested different values of the relaxation parameter to approximate the values of the probability of getting feasible solutions, the expected quality of the solutions, and standard deviation. And based on these measures, they finally selected the optimal value of the relaxation parameter. So this is, in my opinion, is a very nice application demonstration how classical machine learning can be used to enhance, to improve, to design better quantum algorithms. Okay, so now do we have the quantum advantage? So I've already told you and provided the answer on one of the previous slides that perhaps, but it's difficult to prove it. But I would like to show you some publications of other researchers, some notable research laboratories. So the first one is from Google from 2022. And there was an article that said that Google researchers find potential for quantum advantage in machine learning tasks. And here we can read more. So the study showed that quantum machines could learn from exponentially fewer experiments than the number required by conventional experiment, right? So there was an advantage for predicting properties of physical systems performing quantum principal component analysis and learning about physical dynamics. So in this case, the advantage was not in terms of the accuracy of the machine learning model or the speed of training, the compute time, but the advantage was on the number or the size of the training set that was used in the experiment. So that was interesting. There was another paper, this one was co-authored by researchers from IBM, and in principle super polynomial quantum advantage for approximating combinatorial optimization problems via computational learning theory. Right, so here they built on seminal work by Kearns and Valiant. They provided special instances that are hard for classical computers to approximate up to polynomial factors. At the same time, they gave a quantum algorithm that can efficiently approximate the optimal solution within a polynomial factor. And the quantum advantage in this work is ultimately borrowed from the Shor's quantum algorithm for factorizing large numbers. Another example here, there was a quantum or generative quantum eigensolver. There was by using a quantum system to generate data, they later used AI to learn from and guide the generation of more data, and then created a powerful feedback loop that enables breakthrough in diverse fields. So this is what they said. Another announcement, this time from IonQ from the previous year. They announced some new advancements in applying quantum computing to artificial intelligence and machine learning, marking significant progress in hybrid quantum classical approaches that enhance both large language models and generative AI. So they demonstrated how quantum computing can support advanced materials development by generating synthetic images of rare anomalies and enhancing large language models by adding a quantum layer for fine-tuning. So already LLMs with some quantum layers, or one quantum layer in this case. Another announcement, the experiment conducted on the 72-qubit origin Wukong system showed improved model performance. So there was a billion parameter AI model trained using a quantum computer or quantum system after reducing parameters by over 75%. So this was announced in China last year as well. See, here is a paper from this year, exponential quantum advantage in processing massive classical data. So here, they showed some advantages in single-cell RNA sequencing and movie review sentiment analysis, demonstrating 4 to 6 orders of magnitude reduction in size with fewer than 60 logical qubits. So again, it seems that the advantage was in the size of the data in this case. So quantum computers, thanks to what I also presented one of the slides, that we using n qubits, we can actually represent 2 to the power of n bit numbers at the same time. It gives us some new opportunities because classical computers cannot do it. And if you want to start work in the quantum machine learning field, I can recommend some programming frameworks. PennyLane is the most popular and I think the best, or at least the quantum community believes that it's the best framework or library for quantum machine learning. And actually it was the first quantum machine learning library. So when it was released, it was called TensorFlow of Quantum Computing until Google released TensorFlow Quantum. There is also a machine learning module in Qiskit. So Qiskit is in general still probably the most popular quantum computing framework, but PennyLane is considered to be slightly better in terms of the development, ensuring reverse compatibility of different versions of the framework and so on. I do not have it here, but I can also tell you that so all these libraries were in Python, but there's also a programming language that is called Julia, and it's also believed to be a very good programming language for quantum computing and quantum machine learning. So for quantum machine learning, there is a Julia library, popular Julia library that is called YAO.jl. If you want to learn more, here are some useful resources, links to some lectures on YouTube, to some review articles, and a massive open online course by Peter Witek a few years ago. And that's all from my side. So if you're interested in learning more, I will be happy to give you some hints. And if you have any questions, I'll be happy to answer. So thank you for your attention.
So many thanks for this talk. Thanks for giving a kind of a framework for understanding both quantum computing and quantum machine learning. And especially, I think this collection of different resources and overview will be very useful. I would like also to mention about one to some extent popular source of information about quantum computing systems in Poland, because there are at least two strong teams. One in Cyfronet in Krakow, the other one in Poznań Supercomputer Center, involved in quantum computing, and also in Wrocław. So, there was a conference on 45 years of Polish Information Processing Society, and in journal Domena, there was a publication on this, let's say, systems prepared by people from by Kasia Rycerz and colleagues. So if you go there, you can find this. So go to Polish Information Processing System Society, and then to Domena Journal, and the second issue of this Domena will be a good source for this. So now we are open for questions from our colleagues, for questions and for discussion.
Maybe everything was clear.
Well, it was not too complicated. However, usually people have own ideas about quantum computing, because there is always question to which extent the solutions which provide this approach of practical value. So it is maybe you can present your opinion in the meantime before other people will come with our questions.
So it's hard to say. So when I go back to the slide with the progress here, so last year, I think that 2025, this International Year of Quantum, was the year in which there were some breakthroughs, and in particular, I think that D-Wave was probably the first company that announced in a peer-reviewed paper in Science, as far as I remember, that they achieved a practical quantum advantage. By practical, I mean that they were able to solve some scientific problem related to the magnetic field, as far as I remember, for which there was no known classical solution that could give similarly good results, right? So they didn't prove that there is no better classical algorithm, but at least they showed that using a quantum annealer from D-Wave, they were able to achieve results better than all known classical algorithms that have been applied to solve this particular problem by that time. And later there were, as far as I remember, at least one more paper demonstrating this practical quantum advantage published by IBM. So here we already say about some practical advantages, because when we want to tell about some, let's say, theoretical supremacy, then we need to go back to 2019, and maybe some of you remember there was a famous announcement from Google that they demonstrated quantum supremacy. So they solved a problem that normally would take many years for even the best existing classical computer. But first of all, this problem was rather artificial, so it was not a real practical important scientific problem that should be solved to make our world a better place. It was just an artificially designed problem, just designed specifically for this purpose, to demonstrate that we were already able in 2019 to perform some computations on physical quantum computers at that time with 56 qubits or something like that, for which there was no good classical counterpart, classical algorithm. But as I said, it was demonstrated on a rather artificial problem, solving a rather artificial problem. But here, 1 year ago, both D-Wave and IBM announced some advantages in solving some open problems with some scientific importance. So it's I would say that it's still limited. So I would say that these advantages are rather so first they are still questionable, because as I said, there's no formal proof that there are no classical methods for this problem. They are just not unknown, and there are also no proof. But on the other hand, there were some specific problems for which, or at least the authors claim that quantum computers were helpful, which is already quite an important milestone in my opinion. But when we look for such or similar problem, we should mainly look in the domain of chemistry, so simulating some chemical reactions, simulating chemical processes. So this is the domain where we expect the first practical advantages of quantum computers.
Yes, you are definitely right about mentioning this application in computational chemistry, because what can be done with quantum computing? Quantum computing, you can formulate just equation according to, let's say, description of a matter in a quantum way, and you do not need to go to discretization, to all numerical methods, but you can try to solve these equations as they are formulated, because we should know that quantum computers are completely different from computers we are using, because they are, let's say, to some extent not based on digitalization. It is based on, maybe to some extent, they are analog computers which were long ago. So, but these analog solutions, especially in quantum chemistry, can be of great value. Yes.
Mm-hmm. Yeah, exactly. So this domain of chemistry, quantum chemistry, is believed to be the first domain where we should really expect some quantum breakthroughs.
Yes, and this domain of quantum chemistry is also something which is of interest for Sano, because it's quantum chemistry means also better understanding of different type of drugs, and from chemistry to biology is not so far, so it's I think that it is also interesting.
Yeah, this is true.
Yes, and I think that understanding of processes in Brian, which was published by a team in neurocomputing, is also some contribution to this area. So we are still somehow close to what is going on in this area, and I think that definitely it's access to let's say to quantum computers with many qubits is important here. And it's good that CipherNet has such a possibilities with European project. Yes.
Yeah, I can tell you that personally, I also use this access to D-Wave from CipherNet to conduct some experiments with quantum annealing algorithms to solve vehicle routing problem and its variants. So optimizing logistics, routing problems in logistics. Yeah.
Well, we have from Kamil Burkiewicz. It's a question about the adiabatic digital quantum computing.
Yeah, there is a question about prediction concerning the time when quantum computing will be practically feasible. So it depends, right? So as I demonstrated, so D-Wave claimed already 1 year ago that this quantum computer was useful for them to solve a practical scientific problem related to magnetism. But in general, I agree that we are probably still some distance from really practical feasibility. There are some estimates on this. So, for example, I told you about the Moore's law, that there is this density of transistors in the optimal integrated circuits that doubles every 2 years, more or less, now a bit slower. And in quantum computing, we have a similar observation related to quantum volume. And it's observed that quantum volume also doubles more or less once per 2 years or something like that. And I remember that Professor Jakub Milczarek from Jagiellonian University had a presentation about it, that if we, extrapolate the space of advancements, then in about 5 to 10 years, we should achieve, let's say, feasible quantum computers that could give us some advantages, meaningful advantages. But, first of all, the progress in science is rarely linear. So, so it's really hard to say. It's rather from one discovery to another discovery. So,
of course. Anyhow, I don't see more questions. So I think that Paweł, many thanks for your talk, many thanks for discussion and for additional explanation. This seminar will be recorded, available in a few days from now. So if there will be any other question, it will be possible to connect, to ask your question, let's say offline. And it is also a kind of a message for our holiday break, to think about different solutions, different from classical ones we are using here in Sano. So probably the next series of seminars will start in the middle of September, and our plan is to have talks by PhD students who will be in the process of completing their PhD thesis at that time. So it will be a series at least of, if I'm not wrong, about 15 PhD students' presentations in the winter semester. So they will be the most important talks. So many thanks. See you in, let's say, in the middle of September. Thank you very much. Have a good time.
Thank you. Have a good time. Bye-bye.